Let's look at another example of a graphing function. Now let's say if we had the function y equals to 4x over x squared plus 1. Okay, so again, following that guide to curve sketching, first, let's look at the domain of this function. Well, usually for a rational function, we would exclude any values which would make your denominator 0. But in this case, if you look at your denominator, x squared plus 1, that'll never equal to 0 because, again, x squared is always positive or non-negative. Add 1 to it, it's still not going to be 0. Okay, so for our domain, in this case, it's all real numbers from negative infinity to infinity. Okay, let's find our x and y intercepts. Well, to find our y-intercepts, let's let x be 0 and solve for what y would be. So for our y-intercept, we let x be 0, so we'd have y equals to 4 times 0 over 0 squared plus 1. That would equal to 0. So our y-intercept is a point 0, 0. That's also an x-intercept because our x-coordinate is 0 as well. Now for our x-intercept, we will let y be 0, solve for x, so we'd have 0 equals to 4x over x squared plus 1. Now a fraction only equals to 0 if the numerator is 0, so this would imply 4x equals to 0, so x is 0. So the only x-intercept we have is the one that's also a y-intercept. Okay, next we look at the behavior of the graph as x goes to infinity. So we look at the limit as x goes to infinity of 4x over x squared plus 1. Now since the degree of the denominator is larger than the degree of the numerator, this will equal to 0, which will also be the limit as x goes to negative infinity of 4x over x squared plus 1. Okay, now for horizontal and vertical asymptotes. For a rational function, we'd have vertical asymptotes for any value which would make your denominator 0, but not your numerator. But as we mentioned before, the denominator is never going to be 0 for this one, so there are no vertical asymptotes. Now our horizontal asymptote, again, because the degree of the denominator is larger than the degree of the numerator, our horizontal asymptote is the x-axis, which is the horizontal line y equals to 0. Next, we want to see where is this function increasing and decreasing. Well, to do that, we got to find the derivative. So the dy dx equals, well, to find the derivative of 4x over x squared plus 1, we'd have to use the quotient rule. So we'd have our denominator, x squared plus 1, times the derivative of the top, which is 4, minus the top, 4x, times the derivative of the bottom, which is 2x, all over the denominator squared, x squared plus 1, that's squared. So simplifying that, we'd have, 4x squared plus 4 minus 8x squared, all over x squared plus 1, that quantity squared, which equals to 4 minus 4x squared over x squared plus 1, that quantity squared. Now, so this is our derivative. Now, to find where it's increasing and decreasing, we'd first find our critical numbers, which are those values which will make your denominator, which will make the derivative either 0 or undefined. Just like with the original function, this is never undefined, so we got to see when is this equal to 0. Well, again, this is a fraction, so our fraction is equal to 0 only when the numerator is 0. So we set our numerator equal to 0. Let's see, I can factor out a 4. Factor that as a difference of two squares. So the values which will make our derivative 0 are x is 1 and x is negative 1. So we plot those on number line. Let's see, what happens if we plug in 0 for x? Now again, with our derivative, the denominator is squared, so we don't have to worry about the sign of that, because that's always positive. So we just got to see what is the sign of the numerator. So if I plug in 0 for x, we get 4 in the numerator, so that would be positive. If we plug in, let's say, -2, that would be negative. And if we plug in 2 into our derivative, that would also be negative. So we know that our function is decreasing from -infinity to -1 union 1 to infinity. And it's increasing from -1 to 1. And now we got to find where are our relative max and relative mins. Well, as you saw from the number line, using the first derivative, we know it's first decreasing, and then it changes to increasing at -1. So we do know that there is a relative min at -1. And then it goes from increasing to decreasing, so we know there's a relative max at +1. And if we wanted to see what are the actual points for that, plugging in -1 into the function, we would get -2. So we have -1, -2, and when we plug in +1, we get +2. Now looking at the intervals of our concavity, we'd have to look at the second derivative. Now just a reminder that dy dx, our first derivative, was again 4 minus 4x squared over x squared plus 1, that quantity squared. So to find our second derivative, we'd again have to use the quotient rule, and we're also going to have to use the chain rule, as you'll see. So it'll be the denominator, so the x squared plus 1, that quantity squared, times the derivative of the top, which is -8x, minus the numerator, the 4 minus 4x squared, times the derivative of the top, which would be 2, times the x squared plus 1, times the derivative of the inside, which is 2x, all over the denominator squared, so that would be x squared plus 1, now raised to the 4th. Now we could factor out an 8x and an x squared plus 1 from the numerator. And if you do that, well, let's see, so we'd have a negative, let's see, negative x squared plus 1, and then minus, well, let's see, we'd have left on top, let's see, we took out the 4, we took out the, so we'd have 2 times 1 minus x squared. Let's see, all over x squared plus 1 to the 4th, which, let's see, an x squared plus 1 also cancels, so we'd have 8x times, let's see, in the numerator we'd have x squared minus 3 all over x squared plus 1 to the 3rd. So that is our second derivative. Now, again, to find the intervals of our concavity, we got to see when is the second derivative 0 or undefined. Now, just like before, the second derivative is never undefined, so we just got to see when is it 0. So the second derivative is again 8x over x times x squared minus 3 over x squared plus 1 to the 3rd. So we want to see when is 8x times x squared minus 3 equals to 0. So we're saying when is 8x 0, or when x squared minus 3 is 0. So 8x times 0 is 0 when x is 0, and x squared minus 3 is 0 when x equals to plus or minus the square root of 3. So our values are negative square root of 3, 0, positive square root of 3. So again, we could plot those on the number line. Again, square root of 3 is a number between 1 and 2. So let's see, what if we plug in 1 into the second derivative? Again, our denominator is always going to be non-negative, so we just got to see what is the sign of our numerator. And we'd have 8 times negative 2, so that would be negative. And let's see if we plug in negative 1. That would be negative 8 times negative 2, so that would be positive. Let's say, what if we plug in negative 2? So that would be negative 16 times 1, so that would be negative. Now if we plug in positive 2, that'll be 16 times 1, so that'll be positive. So we know that we're concave up from negative square root of 3 to 0 union square root of 3 to infinity. And we're concave down from negative infinity to negative square root of 3 union from 0 to square root of 3. So for 8 to find our inflection points, those occur when x is negative square root of 3, 0, and square root of 3. Now if we plug in negative square root of 3 in for x, what you would get for y is also negative square root of 3. If we plug in 0, you're going to get 0. And if you plug in square root of 3, you'd actually get square root of 3. So now let's bring that all together and get a rough but good sketch of the graph. Okay, so let's first plot some of the points we know. Now, again, our x and y-intercept, the only one was the origin. For our relative max and relative min, that's when we plugged in negative 1 and 1. So when we plugged in 1, as you recall, we got 2. And when we plugged in negative 1, we got negative 2. Now, if we also plug in our inflection points, let's see. Well, one was the 0, 0. Another one was the square root of 3, square root of 3. Now, again, that's a number between 1 and 2, so that would be about right there. And negative square root of 3, negative square root of 3, again, there. Now, using what we know about our concavity, we know that it's concave. Actually, before we talk about the concavity, we know that it's decreasing from negative infinity up to negative 1, then it's increasing, and then it's decreasing after 1. And using that with our concavity, which we know is concave down from negative infinity up to negative square root of 3. So we know it's concave down and decreasing, and we also know that there is a horizontal asymptote at y equals to 0. So the graph of it will look something like that. Then it goes to still decreasing but concave up, and then it's increasing. Then it's going to be concave down and still increasing. Then it's concave down, decreasing. And then it's going to be concave up and decreasing. And again, we have the horizontal asymptote. So we know that it's approaching the x-axis. So this is a pretty good rough sketch of this function.